Hello everybody, welcome to Embetronics. In our previous video, we have seen that what is a bootloader and its need. Then we have designed our custom bootloader. From now onwards, we will start implementing the bootloader and application that we have designed. In this video, we are going to write a simple bootloader that gives control to the application. I am going to create two projects. One is for the bootloader and another one is for an application. As we have two projects, it will give you the two binaries for bootloader and application. We have to place these two binaries into somewhere in the 2 MB flash memory. I am placing the bootloader in the memory 0x08000000. So it is starting from here and stays till here. I have not put all the functions here. I just put the important functions in this image for understanding. The application has been placed in 0x08040000. What will happen when the microcontroller starts? It reads the boot pin. Assume it is 0. Then it starts from the flash memory. We have placed the bootloader in the starting position, so it will read the stack address and store that into the MSB register. Then it takes the reset handler address and jumps to that. Then it does all the memory initialization of data segments and it calls the bootloader's main function. In the bootloader's main function, we will do some other operations. In this example, I am not going to do anything except on off the green LED. Once after that, we have to call the application. How the bootloader will call the application? Because it is a different binary and that application is a different binary, right? Bootloader knows the starting address of the application's vector table. The first 4 bytes have the stack address and the second 4 bytes have the application's reset handler address. So, using the function pointer, we can directly call the application's reset handler. Then the application's reset handler does some initialization and calls the application's main function. In the application's main function, we will be blinking the blue LED continuously. I hope you understood this concept. Even if you don't understand it, this concept is also fine. You will understand this concept while we are writing the code. Now let's make our hands dirty by writing the code. Here we go. I am using the STM32Cube IDE for the development. Frankly speaking, I don't like this kind of IDEs that automatically generates the code. I like to write the code everything from the scratch. Then only I can able to learn properly. But as this is just a bootloader tutorial, we will let this IDE to generate the code for us to save some time. But if you are implementing the bootloader for your project, then I suggest you to use it without this auto-generated code. Okay, fine. Let's start. As I said earlier, I am going to create two projects. First, let's create the bootloader project. Click the Create a new STM32 project. Enter the controller that you are using. I am using STM32F767GI. Select this and click Next. Enter the project name. I am entering my project name as a bootloader and create a separate directory for our convenience. Creating the bootloader project in the bootloader directory. Let's keep the default configuration and click Next. Then click Finish. Okay, it's done. You will get a screen with the microcontroller that we have selected. If you see my board configuration, I have three onboard user LEDs called LD1, LD2, LD3. I am going to use the green LED LD1 for the bootloader and blue red LEDs for the application. Green LED is connected to the PB0, port B0. Click the PB0 and select the GPIO output. Then we want to use one UART for debugging purposes. See here, UART3 is available on PD8 and PD9. This virtual comport is already connected with the onboard debugger. So we don't need any external UART connector like USB to RS-232 TTL converter. Click the PD9 and select UART3 RX. Then click the PD8 and select the UART3 TX. Now we have configured the UART3 pins. Let's enable the UART3. Go to UART3 and set the mode as asynchronous. Okay, we have enabled the green LED and UART3. Save this and give yes to generate the code. Now it is generating the code. Here printf won't work, so we have to redirect the printf to UART3. We will write one function for that. Let's include the stdio.h first. One more thing that I want to tell you. Whenever you are adding your code, you must include your code between the user code begin and user code end. If you add your code anywhere else, then it will be removed when you regenerate the code. Keep this in your mind. After that, I want to add one function to redirect the printf to UART3. This is the function that I am talking about. Whenever you call the printf, it calls the IO putchar function. Inside that, we are transmitting the data to the user3 using the HAL UART transmit function. Now, I want to create the version for the bootloader. For that, I will be creating the macro and one const variable. I will change this macro number whenever I want to change the version number. Let's print something from the bootloader. Then turn on the green LED. Simply I have given 2 seconds delay. I will remove it later. Now I want to call the application. Let's write one function called goToApplication for that. Write the function definition. And declare the function prototype. Let's make it as a static function. Just printing gonna jump to application. Then create the function pointer with no arguments and return type as a void. If you see this image, the application reset handler address will be present over here, which means 0x08040000 plus 4. So we will dereference this pointer to get the reset handler's address and store the reset handler address in the function pointer. Now turn off the green LED to indicate the bootloader is done. Let's call the application's reset handler using this function pointer. If you don't know what is the function pointer and what is the volatile keyword, then please refer to the tutorials that we have posted on our website. Links are available in the description. See the reset handler which has generated automatically. That is loading the stack address to the SP, which is stack pointer. So I don't want to do that again, but some controllers reset handlers might not have this code. So they have to write the stack address manually using the set MSP function. Now the bootloader code is ready. The only problem is if you run this, you may get a hard fault. Do you know why? Any guess? Yes, exactly. We are dereferencing this application's memory and assuming that that has the application reset handler address. But actually the application is not present yet. So it may cause you that problem. We will create an application and place it in that memory. That will solve that problem. We have planned only 64 KB for the bootloader. So let's change it in the linker script. The address is correct, but the length should be 64 KB. Now we are good to go. Let's build. Oh, we got one build error. What is it? Syntax error in the linker script. Okay, this comment syntax is wrong. Let's use the proper one. Build it again. Shall we create the application now? Create another project for the application. Repeat the same process that we did for the bootloader and make sure you are giving different project names. It has been created. Wait a second. I think I made a mistake in the bootloader. In the bootloader, we are not calling the application's reset handler. Instead, we are calling the bootloader's reset handler. The application resides on 0x08040000 and not the 0x08000000. So change that. Some of them might found this mistake while I am writing itself. Sorry, it's my bad. Let's go to the application now. In the application, we will be using the same user3 for debugging purposes and user blue LED 2, which is PB7. Let's enable the user3 and PB7 GPIO as a output. Save and generate the code. We will enable the printf as we did for the bootloader. Then create the macro and variable to hold the application version. Print something. In the while loop, let's blink the blue LED continuously with a 1 second delay. The application is starting from 0x08040000. Let's change that in the linker script, and the length should be 512 KB. That's what we are allocating for the actual application. Now we have to tell the application to use the application's vector table address instead of using the bootloader's vector table address. See here, previously the vector table address is 0x08000000, but once the application starts, the vector table address is 0x08040000. We have to tell the controller about this change. To do that, go to the application source code, core, source, system stm32f7xx.c. Please uncomment the uservec tab address macro. Then set the vector table offset. Right now, offset is 0, which means it is pointing to 0x08000000. We have to change that to 0x08040000. So, just writing 0x40000 is enough. Now, it will point to the 0x040000. Build the application. Got one warning. I missed the type of the variable. Adding the uint8 to that variable. Rebuild it. It has been built successfully. If you see the debug directory, application.bin has been created, and for bootloader, bootloader.bin has been created. Now open the STM32 ST-Link utility software. Let's connect the board with the STM32 ST-Link utility software. Erase the complete chip. See the flash section 0x08000000. It is empty. See the application section 0x08040000. This is also empty. I will disconnect this, and I am flashing these binaries from the IDE itself. First flash the bootloader. Let's check the serial terminal. We got the bootloader prints but not the application print. Why? Check the application's memory. It is empty. That's why the application has not been called. Check the bootloader's memory. See, stack address, bootloader's reset handler's address, and some other interrupt handler's address are there. Now we will flash the application. Go to the application file and flash. By the time I will clear the serial terminal. Can you see this? Bootloader prints and application prints are coming. And check the LEDs also. The time of bootloader starts, the green LED glows, and when the application starts, the blue LED is blinking. Let's verify the memory. Connect the STM32 ST-Link utility software. The bootloader is present and the application is also present. In this tutorial, we have built the bootloader and stored it to the starting of the flash 0x08000000 and stored the application to 0x08040000. In the bootloader's main function, we are calling the application's reset handler function and blinking the blue LED in the main function. In our next tutorial, we will update the application using the bootloader. Sorry guys for this very long video. I tried to keep it short, but if I keep this too short, then I may not explain it clearly. Thanks for your patience and see you in the next video.